Hello friends, welcome back to my YouTube channel. Today it will be 19th part of my discussion on liquid extraction. I will continue my discussion on stage-wise liquid extraction. And today I will be discussing continuous countercurrent multi-stage liquid extraction involving insoluble liquids. So in this case, the feed solution which contains A and C in it, where A is the carrier solvent and C is the solute to be extracted. And this feed solution, it will be contacted with an extracting solvent B. And in this case, in this discussion, A and B, they are considered to be not at all soluble in each other. So A and B, they are not at all soluble in each other. They are not at all soluble in each other. So in my earlier two videos, and that is part number 17 and part number 18, I had discussed continuous countercurrent multistage liquid extraction. But in those discussions, the system that I considered, in that system, A and B, they were partially soluble in each other. Now, in today's discussion, we will be considering a system in which A and B, they are not at all soluble in each other. This A and B are the insoluble liquids that we are talking about. So, in this lecture, you'll learn how to plot the operating line for this operation, then how to find out the number of equilibrium stages in this operation, and then how to find out the minimum solvent rate that can be used in this operation. So let us start the discussion. To begin with, we will summarize about stage-wise liquid extraction. So stage-wise liquid extraction, in stage-wise liquid extraction, the two insoluble liquid phases, that is the feed solution and the solvent, they are contacted in a stage-wise manner. And stage-wise liquid extraction, it is carried out in a stage-wise contact equipment. So in a typical stage-wise contact equipment, there are stages in which the two insoluble phases, they are contacted. So each stage in such a stage-wise contact equipment, it should have a provision, or each stage has a provision to ultimately mix the two insoluble liquid phases, that is the feed solution and the solvent. And the stage also has a provision to physically separate the resulting raffinate and extract phases. So each stage in any stage-wise contact equipment will be having provisions for intimately mixing the feed solution with the solvent, and it will also have a provision to physically separate the resulting raffinate and extract phases. Therefore, typically, each stage is constituted of a mixer and a settler. There are two devices. Two devices in combination forms one stage. Which are those two devices? One is the mixer and the other one is the settler. So, you have the mixer, and then this mixer is followed by a settler, and this combination of these two devices, it forms one stage. Now, in this case, feed is admitted. The feed will be containing A and C in it, and then it is contacted with the solvent phase, and solvent will be containing B. If it is pure solvent, it will be containing just B, and if you are using a recover solvent in the operation, then it will be containing little amount of C in it. It will be containing little amount of C in it if you are using a recovered solvent. So the two phases, the feed and the solvent, they will be first mixed, intimately mixed in the mixer. The resulting mixture will be transferred to the settler, where it will settle into raffinate and extract phases, and then those raffinate and extract phases, they will be physically separated from each other. Now, the case that we are discussing today, where A and B, they are not at all soluble in each other. The meaning is that all A that is used in the system, all A that enters along with the feed, it will remain in the raffinate phase. So raffinate phase will be containing A in it and unextracted C in it. Whereas all B that enters along with the solvent, it will remain in the extract phase. So the extract phase, it will be containing B in it and the extracted solute in it. So this is unextracted solute, and this is extracted solute. The solute in the extract phase, it will be extracted solute, whereas solute in the raffinate phase, it will be unextracted solute. All A, it will remain in the raffinate. All B, it will remain in the extract. No B will enter into the raffinate phase. No A will enter in the extract phase. So the system that we are considering for today's discussion, where A and B, they are not at all soluble in each other. For the system, all A will remain in the raffinate and all B, it will remain in the extract. Now, as per requirement, you can arrange multiple stages. So each stage will be containing a mixer and a settler in it, and you can have this multiple stages. These multiple stages, they can be arranged in a desired cascade. Cascade is nothing but an arrangement of multiple stages in such a way that in a typical cascade, multiple stages, they are arranged so that an output from one stage is an input to the next stage. And two commonly used cascades in the case of liquid extraction, one is cross-current cascade, in which cross-current liquid extraction is carried out. I have already discussed cross-current liquid extraction. I'm giving link to all my videos. I'm giving link to the playlist that contains all my videos on liquid extraction. So one is you have cross-current cascade and the other one is countercurrent cascade. And today we are discussing countercurrent cascade, the liquid extraction that is carried out in countercurrent cascade. So liquid extraction in a countercurrent cascade, we can call it as multi-stage countercurrent liquid extraction. So what is done in this case? Feed is admitted in the first stage and then solvent is admitted in the last stage. And then the raffinate and extract phases, they will be flowing from one stage to the other in a countercurrent manner. So that's why it is a countercurrent extraction. And since you are using multiple stages, you have multi-stage countercurrent liquid extraction. Plus, this operation has to be carried out in a continuous manner, or mostly it is carried out in a continuous manner. And that's why you have continuous multi-stage countercurrent liquid extraction. Okay, now let us talk about N-stage countercurrent liquid extraction. So we are going to consider a countercurrent liquid extraction operation that has N number of stages in it. And the ternary system that we will be considering, the ternary system that is involved in our discussion, it has three components, A, B and C. In this, C is soluble in both A and B. C is the solute to be recovered, A is the carrier solvent and B is the extracting solvent. So A and B, they are not at all soluble in each other. That is, these are insoluble liquids. The feed solution in this case will be containing A and C in it, where C is the solute to be recovered. The solvent, if you are using pure solvent, it will contain just B. It will just contain B if pure solvent is used. But if you are using a recovered solvent, then it will contain B and a little amount of C in it. So B plus C, where C is present in little amount. When this is true, it is true when you are using a recovered solvent. And then the feed solution and the solvent, they are contacted with each other in a N-stage countercurrent liquid extraction operation. And the operation is continuous. The operation will be carried out in a continuous manner. Now let us look at the schematic diagram for the operation. So I am showing some stages in the operation. So this is stage number 1, then this is stage number 2, and I am considering any stage in the cascade. I am calling it as stage n, small n, and the last stage in the cascade is capital nth stage, stage n. Now feed is admitted into stage 1. Feed is admitted into stage 1, and it will be described by these parameters. I will shortly tell you what are these parameters, and then the feed will be moving from one stage to the other. From stage number 1, it will move to stage number 2. From stage number 2 to many stages that are included within these lines. So there will be many stages included in these 2 lines. Then it will be coming to stage number n. Then from stage number 1, again it will move through number of stages before going to the final stage. And then from the final stage, that is n stage, we will be getting the final raffinate. Solvent is admitted to the last stage in the cascade. Then it will be moving from one stage to the other. From n stage, I will tell you what are the notations. From n stage, it will be moving to various stages that are lying within these lines. Then it will be coming to stage n. From stage n, again it will be moving through many stages that are included in these 2 lines. And then finally, it will be coming to stage 2. From stage 2, it will be coming to stage 1. And finally, from stage number 1, we are getting the final extract, which will be identified by these parameters. Then raffinate phase, it will be coming out of stage 1. It will be input to stage 2. From stage 2, it will be going as an input to stage number 3 and many other stages that are included in this line. Then before coming to stage number 1, the raffinate phase must have raffinate comes out of stage number n minus 1. And from n stage, it will come out and it will then pass through many stages that are included between these 2 lines. And then before coming to the final stage in the cascade, it will be coming out of n minus 1 stage. And finally, the final raffinate is coming out of the last stage in the cascade. The extract, it will be coming out of n stage, and then it will be coming out of n plus 1 stage before entering n stage. Then from n stage, it will be coming out and then moving through many stages that are included in these 2 lines. And then the extract that is coming out of stage number 3, it will be entering into stage number 2. Then from stage number 2, the extract that comes out, it is admitted to stage 1. And from stage 1, we are getting the final extract. Now let us understand what are the notations that I am using in my discussion. So in this case, for the feed solution, F represents its mass flow rate, that is mass per unit time. Small xf, it represents weight fraction of solute C in the feed. Capital XF, it represents weight fraction of C on a C-free basis. So this is another way of representing composition of C. I have discussed this type of composition in my earlier videos. I have given link to the playlist. So yes, please, if you have not yet seen those videos, you please watch those videos. And then the solvent phase, the mass flow rate is Sn plus 1, mass flow rate of the solvent. Then Yn plus 1 is weight fraction of C in the solvent, and capital Yn plus 1 is weight fraction of C on a C-free basis in the solvent phase. Then you have the raffinate phase. Raffinate phase that comes out of various stages in the cascade. So here it is the mass flow rates of those raffinate phases. So you have raffinate phase coming out of stage 1, then out of stage 2, out of stage n, out of stage the final raffinate. So R1, R2, R3, so on and so forth, they represent mass flow rates of raffinate phases that are coming out of various stages. Then X, like X1, small x1, small x2, xn, these are weight fractions of C in those raffinate phases. And capital X, all capital X, these are weight fractions of C on a C-free basis, that on a C-free basis in all those raffinate phases. Then you have extract phases. Here all E's, that is E1, E2, E3, they will be mass flow rates of the extract phase that is coming out of various stages. So mass flow rate. Small y is weight fraction of C in those extract phases, whereas capital Y is weight fraction of C on a C-free basis in all those extract phases. So these are the notations that we are using in our discussion. So you please remember all A that enters the operation, it will remain in the raffinate phase, whereas all B which enters into the operation along with the solvent, it will remain in the extract phases. Now let us consider an envelope, the red colored envelope. So this envelope is covering the entire cascade. And now we are going to take material balance for this envelope. First, we will write the steady state total material balance. So if you look at the envelope, feed is entering into the envelope, solvent is entering into the envelope, final raffinate is coming out of the envelope, final extract is coming out of the envelope, and at steady state, since we are considering steady state total material balance, which means whatever material goes into the envelope, same amount of material comes out of the envelope. So the steady state total material balance will be written in this way: F plus Sn plus 1, F plus Sn plus 1, that is equal to mass flow rate of an hypothetical mixture that is considered to be forming within the envelope. So M represents the mass flow rate of that hypothetical mixture, and then this mixture settles into the raffinate phase, the final raffinate phase that is coming out of the envelope, and final extract phase that is coming out of the envelope. So steady state total material balance is written in this way: F plus Sn plus 1, that is equal to M, that is equal to Rn plus E1, and I am calling this as equation number 1. So mass flow rate of feed plus mass flow rate of solvent is equal to mass flow rate of the hypothetical mixture that is considered to be forming in the envelope, that is equal to mass flow rate of the final raffinate that is coming out of the envelope, plus mass flow rate of the final extract that is coming out of the envelope. I am calling it as equation 1. Now let us write steady state material balance for the solute C. So it will be written as F into XF plus Sn plus 1 into Yn plus 1, that is equal to M into Xm, that is equal to Rn into Xn plus E1 into Y1. And if you look at this equation, the equation, okay, let me first rewrite the equation. Now I am rewriting the steady state material balance for the solute in this way: Fxf plus Sn plus 1 into Yn plus 1, that is equal to Rn into Xn plus E1 into Y1, and I am calling this as equation number 2. So this is total feed into fraction of C, total solvent into fraction of C, total raffinate into fraction of C, total extract into fraction of C. And in the previous equation, we have the total flow of the mixture, hypothetical mixture, into fraction of C in that mixture. So we have got equation number 1 and equation number 2. Now let us move ahead. Now equation 2, we got F into Xf plus Sn plus 1 into Yn plus 1, that is equal to Rn Xn plus E1 Y1. Now we are going to analyze each of the term that is involved in this equation. Let us start with the first term. This term is concerned with the feed solution. So feed solution that enters the operation, it contains A and C in it. So if you have to express it in a mathematical form, you can write this. Mass flow rate of feed is equal to mass flow rate of A plus mass flow rate of C in it. And a mass flow rate of C in it is nothing but a fraction of C in it into feed flow rate. That means this equation can be written as F is equal to A plus XF into F. Now I will bring this term to this side. So it will be F minus XF into F, that is equal to A. Then I can take F common. So F into 1 minus XF, that is equal to A. Then I will bring this term to this side. So it will be F is equal to 1 upon 1 minus XF into A. And that is, if I multiply with XF on both the sides, I will be getting this. F into XF is equal to XF upon 1 minus XF into A. So why I am doing this? Because I want to get replacement for F into XF, that is present in equation number 2. Now, as per the definition for weight fraction of C on a C-free basis, this ratio, that is small xf upon 1 minus small xf, is capital XF. That means F into a small xf is A into capital XF. That is in equation number 2, the term F into XF, it can be replaced with A into capital XF. Then for the solvent will be containing B and C in it. That is, mass flow rate of solvent is equal to mass flow rate of B in it plus mass flow rate of C in it. And how do you get mass flow rate of C in it? I'll show you. So this is Sn plus 1 is equal to B plus Y n plus 1 into Sn plus 1. So this is the mass flow rate of C in the solvent. And then I can bring this term on this side. So it will be Sn plus 1 minus Yn plus 1 into Sn plus 1, that is equal to B. Therefore, Sn plus 1 can be taken out as a common term. So this will be Sn plus 1 into 1 minus Yn plus 1, that is equal to B. Then I'll bring this term to this side. So it will be Sn plus 1 is equal to 1 upon 1 minus Yn plus 1 into B. And if I multiply with Yn plus 1 on both the sides in order to get this term, so it will be Sn plus 1 into Yn plus 1 is equal to Yn plus 1 divided by 1 minus Yn plus 1 into B. But a small Yn plus 1 divided by 1 minus small Yn plus 1 is capital Yn plus 1. Therefore, Sn plus 1 into Yn plus 1 is equal to B into capital Yn plus 1. That means I can replace this term that is present in equation 2 with the term B into capital Yn plus 1. Okay, now let us look at the raffinate phase. Raffinate phase, it will be containing all A and C in it. So mathematically this will be written as mass flow rate of raffinate is equal to mass flow rate of A plus mass flow rate of C. That is, Rn is equal to A plus mass flow rate of C in the raffinate. It will be given as small xn into Rn. Then I will bring this term on this side. So it will be Rn minus xn into Rn, that is equal to A. Then Rn can be taken out as a common term. So it will be Rn into 1 minus xn, that is equal to A. That is, Rn is equal to 1 upon 1 minus xn into A. And in order to get this term, I will have to multiply with xn on both the sides. So it will be Rn into xn, that is equal to xn upon 1 minus xn into A. But small xn upon 1 minus small xn is capital Xn. That means Rn into xn will be equal to A into capital Xn. That is, the term Rn into xn can be replaced with A into capital Xn. Now let us look at the extract phase. Extract phase, it will be containing all B in it plus solute. So mass flow rate of the extract is equal to mass flow rate of B in it plus mass flow rate of C in it. And that means this is E1 is equal to B plus Y1 into E1. Mass flow rate of C in it is given as Y1 into E1. Then I'll bring this term to this side. So it will be E1 minus Y1 into E1, that is equal to B. And if I take E1 common, so it will be E1 into 1 minus Y1 is equal to B. And that in the next step, E1 will be 1 upon 1 minus Y1 into B. And in order to get this term, I will multiply with Y1. So it will be E1 into Y1, that is equal to Y1 upon 1 minus Y1 into B. but small y1 upon 1 minus small y1 is capital Y1. Therefore, E1 into Y1 is equal to B into capital Y1. That means I can replace E1 into Y1 in equation 2 with B into capital Y1. Okay, so we got this relations. F into small xf, that is equal to A into capital XF. Sn plus 1 into small yn plus 1, that is equal to B into capital Yn plus 1. Rn into xn, that is equal to A into capital Xn. And E1 into small y1, that is equal to B into capital Y1. Now we are going to use this in equation 2. So if we use in equation 2, we will be getting A into xf. Xf is replaced with AXF plus B into Yn plus 1. Sn plus 1 into small yn plus 1 is replaced with B into capital Y plus Yn plus 1. That is equal to A into Xn plus B into Y1. Now, I will bring all terms containing A on one side and all terms containing B. I will take those terms to the other side. So, it will be A into XF minus A into Xn, that is equal to B into Y1 minus B into Yn plus 1. Then I can take E common on this side. So, it will be A into XF minus Xn, that is equal to B into Y1 minus Yn plus 1. That is, it will be A upon B is equal to Y1 minus Yn plus 1 upon XF minus Xn. I am calling this as equation number 3. And what can you say about equation number 3? It represents a straight line. It passes through the point XF Y1 and Xn Y1. So, actually, it is a straight line on the XY plot where you are plotting X against capital Y, which are in equilibrium with each other. So, on that plot, equation number 3 will be a straight line, and that will be having one end with this coordinates xf y1, and the other end will be having the coordinates of xn yn plus 1. Now, if you look at equation number 3 on the right hand side, so in the numerator, we are subtracting y coordinate of this point from the y coordinate of this point. And in the denominator, we are subtracting x coordinate of this point from the x coordinate of this point. So, there is no need of rearranging it. The equation number 3 is already present in an appropriate form. So, it will be a straight line that passes through these 2 points, and in the slope of this line will be A upon B. So, this line, the operating line for the countercurrent liquid operation, countercurrent liquid extraction, the operating line will be having a positive slope. Now, we will understand this when we plot the operating line on the XY data. So, now let us plot the operating line. So, for that we will be using the equilibrium diagram where Y is plotted on the y-axis, capital Y is plotted on the y-axis, and capital X is plotted on the x-axis. So, when you plot the equilibrium values, you will be getting the equilibrium curve. Now, let us first locate the endpoints. So, one in y coordinate of one endpoint is Yn plus 1. And the x coordinate for that point is xf. That means xf represents the feed. So, you are starting at the end in which, at the end where feed is entering. And this point represents the end at which solvent is entering into the operation. So, after the feed enters into the operation, the concentration of C is going to decrease from xf to xn. Whereas, when solvent enters with concentration Yn plus 1, as it moves through the cascade, the concentration is going to increase to Y1. So, feed enters with this composition, and raffinate, it comes out with this composition. Solvent enters the operation with this composition, and it comes out as an extract phase with this composition. So, I will just draw these lines, these dashed lines for our reference. Now, let us look at this point. What are the coordinates of this point? the coordinates are xf, y1. The coordinates of this point are xf and capital XF and y1. So this point represents the end where feed is entering into the cascade. Whereas if you look at this point, the coordinates of this points are xn, yn plus 1. So this point is representing the end where solvent is entering into the operation, or where final raffinate comes out of the operation. This point represents this end. This point represents the end at which feed is entering into the operation, or final raffinate is coming out of the operation. So having understood the location of these points, the operating line has to be of this nature. The slope, the operating line, let me just erase it. So the operating line would be having a positive slope. And what is the slope? Slope of this line is A upon B. And it will be lying below the equilibrium curve. For mass transfer from feed to the solvent, the operating line will be lying below the equilibrium curve. So in this way, you have to plot the operating line on the XY diagram or the equilibrium diagram. Now let us learn how to get the number of equilibrium stages. Equilibrium stages, or you can call them as ideal stages or theoretical stages. Now let us learn how to get the number of those equilibrium stages. So for that we will be using the XY diagram, that is equilibrium diagram, where we have plotted the operating line. So you have to start at the end where feed is entering into the cascade. So it enters, this point is representing that end. So you start at this point, travel a horizontal distance, go to the equilibrium curve. Once you reach the equilibrium curve, come down vertically to the operating curve, then travel horizontally to the equilibrium curve, come down vertically to the operating line, to the equilibrium curve, 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 and finally to the operating line. So you are going to draw this triangles till xn is crossed. And number of triangles that you draw in this process, it represents the number of equilibrium stages that are to be used in the operation, multi-stage countercurrent liquid extraction operation. So in this case, for this particular diagram, there are 1, 2, 3, 4, 5, 6 and 7 stages. So in this way, you have to find the number of equilibrium stages required in a typical multi-stage countercurrent liquid extraction operation. Okay, so the other thing that we will be learning today is we will know how to get the minimum solvent rate that can be used in a typical multi-stage countercurrent liquid extraction operation. So for that, we will be using the equilibrium diagram. Now one end of the operating line is fixed. So the operating line will be starting at this point. Now I am drawing an operating line in such a way that it either touches the equilibrium curve in one point, in a single point, or it intersects the equilibrium curve in a single point. So for example, I have drawn the operating line which is touching the equilibrium curve over here, and then I have extended it so that it intersects the vertical line that I have drawn through XF. So this is the operating line that will give me the minimum rate of solvent that I can use in the operation. So when I draw such a line, I am interested in knowing the y coordinate of the point at which it intersects the vertical line through XF. And this is the y coordinate. And I am calling it as y1 max. I am going to use it because that will be useful for me in finding the minimum solvent rate. So in this case, the slope of the operating line, slope of such a operating line will be A upon B minimum. And the slope, the quantity of B that will be used, it will be the minimum possible solvent rate. So we know slope is given by this equation. A upon B is equal to y1 minus yn plus 1 divided by xf minus xn. We have got this equation previously. Now, if I replace y1 with y1 max, B will become B minimum. That's it. So, A upon B minimum will be y1 max minus yn plus 1 divided by xf minus xn. And if I solve this, everything will be known to me except B minimum. So, I can solve this equation and get B minimum. That will be the minimum solvent rate that can be used in this operation. So, in order to find the minimum solvent rate, you need to draw a operating line that will intersect the equilibrium curve or touch the equilibrium curve in one point. Because when such a line intersects the vertical line through x, I'm going to get y1 max, and I will be using y1 max in the equation for the slope of the operating line to get the minimum solvent rate that can be used. So with this, I end my discussion for today's topic. Here I have discussed multistage countercurrent liquid extraction operation, continuous multistage countercurrent liquid extraction operation, in which you have minimum solvent. In which you have insoluble liquids. That is, you have a feed solution containing A and C in it, which is contacted with B, and A and B, they are not at all soluble in each other. So first we learn how to write the material balance, then how to get the equation for the operating line, how to plot the operating line on the equilibrium diagram, then how to find out number of equilibrium stages, or you can say number of ideal stages or number of theoretical stages, then how to get the minimum solvent rate that can be used in such multi-stage countercurrent liquid extraction. So with this, I end my discussion for this particular video. I hope you must have understood how to get the number of equilibrium stages, then how to plot the equilibrium curve, how to plot the operating line, then how to get the minimum solvent rate that can be used in the operation. In my next video, I will be discussing one numerical that is based on today's topic. So thanks for watching the video. Thanks for watching my video. Do subscribe to my channel. Tell your friends to subscribe to it. Hit the bell icon so that you'll be notified as soon as I upload any new video on my YouTube channel. In my next video, I will be discussing a numerical where I'll be telling you how to get the number of equilibrium stages and how to get the minimum solvent rate. And I'm sure you'll be joining me in my next video. For now, have a nice day. Thank you and bye-bye.